meter prover, inline calibration for continuous traceability and legal verification. The meter prover is a fundamental component of the Fiscal metering system, providing direct calibration of turbine meters under live process conditions. Its purpose is to establish the actual meter K factor by comparing measured pulse counts against a known traceable volume, ensuring the turbine meters operate within acceptable uncertainty limits over time. The prover must be designed as a mechanical displacement type, either unidirectional or bidirectional. Bidirectional provers are typically preferred for their compact footprint and balanced pressure dynamics, especially in offshore or space-constrained environments. Where approved by relevant authorities, compact provers may be used in place of traditional configurations, provided they demonstrate equivalent accuracy and repeatability. The prover must include a quick opening closure to facilitate safe and efficient insertion and removal of the prover sphere, or piston. The number of pulses counted during one calibrated run must exceed 10,000 to ensure high resolution in the K-factor calculation. Detector systems used to define the start and stop of the prover volume must be repeatable to a resolution compatible with this pulse density. The sphere velocity must not exceed 3 meters per second to prevent hydraulic shock and ensure uniform travel. At each end of the calibrated section, dual redundant detector switches must be installed to proving interruption in the event of a single detector fault. These switches must be precisely aligned and tested during manufacturing to maintain the consistency of the calibrated volume, regardless of future detector replacements. Detectors must be designed to reliably actuate at all flow conditions, with suitable ingress protection and environmental durability. For bidirectional provers, a 4-way flow diverter valve must be installed to reverse the direction of the fluid and the sphere. This valve must operate with minimal turbulence or pressure disruption and maintain tight sealing to avoid volume leakage or bypass during the proving run. The valve's position must be monitored continuously, with leakage alarms tied into the prover control system. The prover must include provisions for external recalibration using a master prover or calibrated master meter. This includes flanged ports or bypass lines for loop-in verification, ensuring the long-term validity of the prover's own reference volume. Internal surfaces of the prover must be coated with a durable, non-porous lining to ensure a smooth, consistent bore over time. The coating must withstand the process fluid, pressure cycles, and potential decompression effects. All surface preparation, application, and repair procedures must be documented and traceable. Mechanical components, such as guide bars and tees, must be designed to support the smooth transit of the prover sphere without deformation, misalignment, or abrasion. These elements must be precisely machined to avoid interference with the detector switches and to maintain uniform contact between the sphere and the prover bore. Together, these design features ensure that the meter prover delivers repeatable, traceable calibration of turbine meters, forming a critical foundation for legal metrology compliance, quality assurance, and high-integrity custody transfer. Monitoring and control system, digital oversight and distributed computation for fiscal metering, stream microcomputer, dedicated meter run control, and real-time computation. Each metering stream must be controlled and monitored by an independent stream microcomputer. This unit is dedicated solely to functions associated with fiscal measurement and must not perform unrelated control or communication tasks. The stream microcomputer acts as the primary interface between the turbine meter, associated transmitters, and the overall station control architecture. The stream microcomputer must receive dual pulse inputs from the turbine meter pickups and execute real-time pulse integrity verification. These checks must detect any discrepancies in pulse timing or count that could indicate signal degradation, pickup failure, or meter malfunction. The system must comply with industry-recognized standards for pulse verification, including detection of missed, duplicated, or distorted pulses. The microcomputer must support manual or automated entry of the meter K factor, pulses per volume unit. This factor is applied in calculating gross volume flow, which is then compensated using live pressure, temperature, and density inputs to determine mass flow and standard volume at reference conditions, e.g. 15 degrees Celsius and 101.325 kilopascal. All calculated variables, gross volume, mass flow, corrected volume, and running totals must be locally displayed and stored. Displays must be clear, unambiguous, and of sufficient resolution to verify compliance with calculation precision requirements. Additionally, the stream microcomputer must permanently display the accumulated mass quantity with enough digit capacity to record at least 3 months of maximum flow without rollover. Daily totals must also be recorded, resettable only at specified intervals. Each unit must allow the operator to retrieve previous meter factors and log events related to meter proving, parameter changes, and alarms. The microcomputer must distinguish between automatic and manual operating modes, particularly during proving or system override conditions. In case of failure or maintenance, the stream microcomputer must be hot swappable, with plug-and-play capabilities that retain configuration and measurement continuity. Manual parameter entries, such as new meter factors or set points, must not be rounded or truncated on display or storage. Timestamping of all parameter changes and event logging is mandatory to support full audit traceability. The stream microcomputer must communicate with the station computer over a secure, high-reliability digital link. It must also support standard communication protocols for real-time data sharing with supervisory systems. Local alarm outputs must be issued in the event of meter failure, pulse loss, invalid parameter values, or flow detected while the stream is deselected. Station microcomputer centralized aggregation, reporting, and operator interface. The station microcomputer serves as the central control node for the Fiscal metering system. It must collect, process, and display data from all stream microcomputers and manage system-level functions such as sampling, net oil computation, alarm processing, and reporting. The station microcomputer must include a high-visibility alphanumeric display capable of presenting live data, system alerts, and operator prompts. A secure keyboard or touchscreen interface must allow for command input, configuration updates, and alarm acknowledgement. All entries must be access controlled and time-stamped. Its core function is to poll the stream microcomputers and build a comprehensive database of measured and calculated values, including gross volumes, mass flow rates, standard volumes, densities, temperatures, and pressures. From this data, the station computer must compute station-wide totals and summaries, including the cumulative mass and volume flow across all active meter runs. The station microcomputer must support both periodic and on-demand report generation. Reports may include hourly or daily totals, event logs, alarm histories, and meter proving records. A dedicated printer interface must be available to produce hard copy records compliant with audit and custody transfer requirements. Integration with SCADA or DCS systems must be supported via a configurable communication link. This link must allow for two-way data exchange, including set point control, alarm status, and summary reporting. Protocols used must be widely supported and approved by the system integrator for compatibility. The station microcomputer must also manage auxiliary control functions such as sampler actuation, water cut sensor switching in case of duty standby operation, and flow proportional sampling logic. Valve status monitoring, alarm forwarding, and user override functions must be fully integrated within the station interface. The system must be capable of running in an interactive mode, guiding operators through workflows such as proving sequences, meter selection, and fault recovery. A complete index of available commands and functions must be accessible to the operator, ensuring usability and operational transparency. The station microcomputer must permanently record the station-wide accumulated totals with adequate resolution to log extended periods of operation. These totals must be immune to reset or loss during normal operations and remain recoverable following power outages or communication disruptions. Prover microcomputer, automated calibration logic for K-factor validation and sphere control. The Prover microcomputer is responsible for managing all meter proving operations, ensuring that turbine meters are continuously calibrated to traceable standards without interrupting flow. It must operate in conjunction with the stream and station microcomputers and be capable of standalone functionality in case of partial system faults. The Prover microcomputer must initiate and control the entire proving sequence. This includes receiving a proving command, automatic, semi-automatic, or manual, checking system readiness, and initiating sphere launch or flow reversal based on current valve positions, flow rate stability, and process conditions. It must verify that prover inlet and outlet temperatures and pressures are within allowable limits before commencing a run. During the proving cycle, the microcomputer must count raw, unscaled pulses from the turbine meter between detector switch activations. These counts are used to compute the meter K-factor, pulses per unit volume, based on the known prover volume corrected to actual flowing conditions. The prover microcomputer must be capable of performing a series of proving runs, automatically terminating the sequence once a sufficient number of consistent results are achieved. Typically, 5 consecutive runs must fall within a total spread of less than 0.05% to be considered valid. If proving results deviate beyond this threshold, the system must continue up to 10 runs before aborting the sequence and raising an alarm. Failed runs must be logged, annotated, and retained for audit purposes, even if they are excluded from the final calibration outcome. Following a successful proving sequence, the newly calculated meter factor must be displayed for operator review. Upon approval, the factor must be automatically or manually downloaded to the corresponding stream microcomputer. The previous factor must remain stored for historical comparison, and any changes must be timestamped and recorded with operator identification. The prover microcomputer must control all relevant field equipment, including stream flow control valves, prover four-way diverter valves, and isolation valves. It must monitor valve seal status, position feedback, and detector switch health. In the event of any valve misalignment, leakage, or failed sensor, the system must abort the proving sequence, initiate alarms, and prevent further proving until the issue is resolved. A resettable high-speed totalizer must be provided to accumulate pulse counts with a minimum resolution of pi-1 pulse and capacity for extended proving runs. All pulse inputs must be digitally filtered to reject noise while preserving accuracy. Input signals must include detector switch activations, prover inlet and outlet temperatures, prover pressure, valve position and seal integrity status, raw turbine meter pulses. Output signals must include stream control valve commands, prover four-way valve actuation, serial data exchange with stream and station microcomputers. Alarm and validation report generation. The prover microcomputer must support direct printing of validation reports, including meter ID, date, time, flow conditions, K-factor results, number of runs, deviation spread, and any annotations related to abnormal conditions. This reporting capability ensures transparent traceability and supports compliance with fiscal metrology standards. Overall, the prover microcomputer must deliver high accuracy calibration, system-level coordination, and rigorous documentation, enabling the metering system to maintain traceable accuracy across operational cycles and over time. Data integrity and security, system reliability, access control, and traceable operations. The monitoring and control system must enforce strict data integrity protocols to ensure that all fiscal measurement operations are accurate, secure, and tamper-evident. Both logical and physical integrity of the microcomputer network must be continuously monitored and verifiable through built-in diagnostics, audit trails, and user access management. Each microcomputer, stream, station, and prover must be equipped with self-diagnostics capable of detecting internal hardware faults, communication errors, and abnormal operating conditions. These diagnostics must generate alarms and provide detailed feedback to the station microcomputer, enabling prompt isolation and resolution of faults. If a stream microcomputer fails, the system must automatically deactivate the associated meter run and prevent the use of invalid data. If a data link failure is detected between system components, the fault must be clearly enunciated without affecting the standalone operation of individual devices. Security architecture must restrict access to sensitive functions such as meter factor changes, parameter configuration, calibration initiation, and diagnostic overrides. Access must be limited to authorized personnel via password protection, key switches, or electronic authentication. All access attempts, successful or failed, must be logged with timestamps, user identification, and the specific action performed. Each release of the Fiscal application software must be assigned a unique version number, visible both on the system display and on printed reports. Installation of new software or firmware must be traceable, including the name of the person performing the update, the date and time, and the reason for the change. Any modified configuration parameter must be recorded with both its as found and as left values to ensure full transparency and reversibility. Malfunction of any data link to external supervisory systems, e.g. SCADA or DCS, must not interrupt the core fiscal functions of the individual microcomputers. Each device must continue local processing, retain data, and log events independently, with resynchronization once communication is restored. Manual data entries must be validated before being accepted by the system. Alarms must be triggered for data or configuration values that exceed expected operating ranges. Analog inputs must include soft limits near zero and full scale to detect sensor failures, wiring faults, or signal corruption. These soft limits ensure that invalid readings are caught early, preventing erroneous calculations and downstream reporting errors. An event log must record all changes in system status, including logins, parameter edits, proving actions, alarm acknowledgements, and system resets. This log must be non-volatile, retrievable via operator interface, and printable for audit and compliance purposes. The log serves as a full traceability mechanism, ensuring measurement accountability under both normal and abnormal conditions. Together, these integrity and security measures provide a resilient framework that preserves fiscal data accuracy, defends against unauthorized access, and supports the full auditability required in custody transfer and regulatory environments. Factory and field inspection and testing, validation of design, performance, and compliance across system lifecycle. General inspection. All turbine fiscal metering systems must undergo thorough factory and field inspection to confirm compliance with design specifications, performance criteria, and applicable regulatory requirements. The manufacturer must notify the principal in advance of any scheduled tests, allowing sufficient time for witness attendance by the client, third-party inspectors, or regulatory authorities. The inspection scope must include mechanical fabrication, instrumentation accuracy, software functionality, and system integration. If specified in the project documentation, formal approval by metrology authorities may be required before shipment, covering design reviews, calibration results, and installation compliance. Inspection for metering design compliance. Each turbine meter and associated meter tube must be inspected prior to assembly to verify compliance with dimensional tolerances and installation geometry. This includes upstream and downstream pipe lengths, the placement of flow straighteners, and positioning of temperature and pressure tappings. Turbine meters must be accompanied by a calibration certificate issued by an accredited facility. Calibration must be traceable to national or international standards, and when possible, performed with fluid properties similar to the intended process conditions. If testing with process fluid is not feasible, calibration using water is acceptable, provided the manufacturer supplies validated correction factors for fluid viscosity and density. The prover system must also be calibrated by an independent, accredited laboratory and must meet traceability requirements to establish its reference volume. Witnessed verification by the principal or metrology authority is often required and must be documented on a formal certificate. Instrumentation, including temperature transmitters, pressure transmitters, densitometers, and water cut meters, must be tested according to defined procedures. This includes accuracy verification, range validation, and response behavior under simulated process conditions. Piping system inspection and testing. All materials used in the pressure retaining system, piping, fittings, and valves must include mill certificates and traceability documentation. Prior to fabrication, welders must be certified to the applicable project specification. Weld inspections must be carried out as per project quality standards, including visual, radiographic, or ultrasonic testing as required. Hydrostatic testing must be performed on the fully fabricated pipework to confirm structural integrity under pressure. Turbine meters must be removed and replaced with spool pieces during testing to avoid damage. The entire system must be held at test pressure for a defined period, with pressure and temperature recorded on certified charts. All joints must be leak-free, and flange alignment must be maintained without pipe stress or deformation. Flange connections and swing joints must be operable without pipe spring or forced misalignment. Random spot checks may be conducted at the principal's discretion to verify proper assembly. Electrical safety testing. All electrical wiring must undergo insulation resistance, earth continuity, and ground fault testing. To avoid damage, sensitive instrument devices must be disconnected prior to insulation testing and reconnected afterward. Each junction box, termination point, and instrument housing must be verified for correct assembly, proper sealing, and compliance with hazardous area requirements. Explosion-proof and intrinsically safe devices must include documentation confirming compliance with hazardous zone classifications. Cable segregation, grounding systems, and earthing points must be inspected to ensure electrical safety and system reliability. Calibration facilities and support equipment. When specified, the manufacturer must provide a complete suite of calibration tools and verification standards for field use. This may include temperature baths for RTD verification, deadweight testers for pressure transmitter calibration, reference fluids for densitometer checks, known water cut blends for inline meter validation, portable communicators for digital transmitter interrogation. The gravitational constant at the site location must be calculated for pressure calibration accuracy using deadweight testers. Reference standards must have valid calibration certificates with measurement uncertainty no greater than 1/3 that of the instrument being calibrated. Mass and volume computation system testing. Functional testing must verify that the control system correctly processes all measurement signals, converts them to digital values, and performs volume and mass flow calculations accurately. Simulated signals must be used to verify alarm thresholds, meter totalization, and data reporting. Interfaces to the printer, SCADA, DCS, and other systems must be validated. Tests must also confirm that system diagnostics detect short circuits, failed channels, or abnormal values. Auto restart functionality following power failure, proper alarm generation, and secure parameter entry must be demonstrated. Spare parts and system tools must be inserted and tested in the actual configuration to ensure compatibility and readiness. Heat soak and stability testing. The complete metering system, including control electronics, must undergo extended heat soak testing at elevated temperatures, typically 45 degrees Celsius, for at least 100 hours. During this period, a representative load of digital and analog signals must be simulated continuously. Environmental cycling between ambient and elevated temperatures must be applied in intervals to simulate site conditions. All system functions, data acquisition, reporting, alarms, and calculations must be periodically triggered during this test to verify system reliability under stress. Any component failure during testing requires replacement and repetition of the entire heat soak sequence. Dynamic functional testing. Dynamic tests must validate real-time interaction between system components. This includes automated proving sequences, flow control valve response and modulation, alarm generation under simulated failure conditions, meter selection and deselection logic, valve positioning and seal integrity checks, water cut system switching, signal transmission between skids and control system. Alarm conditions, log files, and operator interface behavior must be tested in full. All event reporting formats must be demonstrated, confirming compliance with documentation and audit standards. Wet functional testing. The fully assembled metering system must be tested with flowing liquid, typically water, to demonstrate complete functionality under realistic flow conditions. This includes proving loop operation, signal verification, flow modulation, sampling system actuation, and system response to varying flow rates. Temporary pumps, tanks, and circulation piping must be used to simulate full-scale operation. Following the test, the system must be flushed and dried using warm compressed air or nitrogen. Material compatibility and corrosion prevention must be considered during cleaning. Site acceptance testing. Once installed at the final location, the system must undergo a formal site acceptance test. This test validates that the system, as installed and commissioned, functions correctly with the live process fluid and communicates seamlessly with the facility's supervisory systems. The SAT includes proving, live flow verification, alarm testing, and full integration validation. It is the final step before the system is certified for fiscal service.